Double displacement reactions is going to be the topic in this lesson, and we'll learn that they're also called double replacement reactions, or exchange reactions, or metathesis reactions. And we're going to learn about the three major types, and that's going to be precipitation reactions, acid-base neutralization reactions, and one special gas-forming reaction. And then we're also going to go through talking about like the molecular equation versus the ionic equation versus the net ionic equation, which removes the spectator ions. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, in addition to high school and college science prep, we also do DAT, MCAT, and OAT prep as well. You can check out those courses at chadsprep.com. Now, this lesson is part of my new general chemistry playlist. I'll be releasing several lessons a week throughout the school year, so if you want to be notified every time I post a new one, subscribe to the channel and click the bell notification. Let's get into this. And so, as I said there in the intro, double displacement reactions are also called double replacement reactions, or exchange reactions, or metathesis reactions, and you should probably know all the names. But you're probably going to either see double displacement or double replacement more often than the others, but you should definitely know them all. And this is an example of an aqueous reaction. What you should know is that we're just going to have cations and anions trading partners. So notice, typically in an ionic compound, you write cation first, anion second, cation first, anion second. And so this cation is going to end up with this anion in the products, and then this cation will end up with this anion in the product as well. And so if we form a solid, we'll end up calling that a precipitation reaction. If your reactants are an acid and base, we'll call that an acid-base neutralization. And if it's one special case that results in the production of a gas, and specifically we'll look at one that produces carbon dioxide gas, then that'll be our gas-forming double displacement reaction. Let's take a look at precipitation reactions. So the first type of double displacement reaction we're going to take a look at is called precipitation reactions. And again, the hallmark of those is you actually form a solid. So one of your products is a solid. And in this case, we're going to have these two lovely species be our example, trading cations with anions. And we have to predict products oftentimes. And so you just want to take the cation of one and combine it with the anion of the other. And so here it's going to be lead and iodide. And to predict the proper formula here, you've got to know the charges. And so you can see lead here. So it doesn't always take on the same charge. And so you have to figure out what charge it is in this context. And in this case, with two nitrates, which are -1 each, lead must be +2. And iodide, as a monatomic ion, is -1. And so if lead's +2 and iodide's -1, to get a neutral compound, like we learned back in chapter 2 for ionic compounds, we're going to need 2 iodides for every lead. And so the proper formula for the product is PbI2. Now, just because sodium iodide only has 1 iodide per formula unit doesn't mean that our product has to be the same. They don't have to match at all. It all comes down to forming neutral compounds. Now, in this case, we'll also combine now sodium, the cation of this one, with the anion of this one, nitrate. And in this case, sodium's +1 based on where it's located at the periodic table, and nitrate, again, as a polyatomic ion, you're supposed to memorize as -1, and that's the formula for sodium nitrate. And once again, even though lead nitrate has 2 nitrates per formula unit, sodium nitrate's only going to have 1, again, just based on forming neutral ionic compounds. All right, so now we got to balance this thing, and in this case, I can see 1 lead on both sides. I can see 2 nitrates on this side. To get 2 nitrates on this side, we're going to have to put a coefficient of 2 right here. That's also going to give me 2 sodiums. So to get 2 sodiums on this side, we'll have to put a 2 right here. And now we have 2 iodides and 2 iodides, and this thing is balanced. All right, so I gave you the phases of the reactants, and for a typical double displacement reaction, both your reactants are typically going to be aqueous. So, but your products here, you're going to have to figure out based on the solubility rules we took a look at in the last lesson. So if we start with PbI2, you guys learned that most chlorides, bromides, iodides are soluble, except silver, lead, and mercury. So because this is an exception to being soluble, it's insoluble, and insoluble compounds are in the solid phase. All right, then for sodium nitrate, we learned that all nitrates are soluble, period, no exceptions. And so for soluble compounds, we'll write aqueous. All right, so we often refer to this as our molecular equation. So from this molecular equation is where we can see that we get this name double displacement or double replacement, where the cations and anions are just trading partners. But it turns out it's a little more complex than that, and we'll see that when we go to the ionic and then the net ionic equation to see what's really going on. Now, one other thing you should realize, you kind of visualize what's going on here, is you've got two aqueous solutions. And it turns out both of these are colorless aqueous solutions. But when you form lead iodide here, I believe it is a white precipitate, and so all of a sudden you go from two clear solutions, and when you mix them, it all gets milky white. And if you wait long enough, that milky white, the white stuff will actually settle onto the bottom as a white solid. And that's the evidence you've got a precipitation reaction. All right, so next thing I want to do is identify who are the strong electrolytes in this reaction. And so in this case, you remember your strong electrolytes are either soluble ionic compounds, strong acids, or bases. And so in this case, we've got a soluble ionic compound here. Again, it's ionic and it's aqueous. And again, the key is to be a soluble ionic compound, you've got to be ionic and aqueous. But don't think that everything aqueous is going to be a strong electrolyte. It's got to be a soluble ionic compound or a strong acid or a strong base. But you could have like a weak acid or a weak base, which are still going to be aqueous, but are not going to be strong electrolytes. So be careful. It's not everything that's aqueous ending up being a strong electrolyte, but it is going to be most things. But this one is aqueous and it is ionic, so that makes it a soluble ionic compound, so it's going to be a strong electrolyte. Sodium iodide, same thing. It's ionic and it's aqueous, that means it's soluble, and so it's one of the soluble ionic compounds and is a strong electrolyte. But lead iodide, even though it's ionic, it is not aqueous, so it's not soluble. It is not a strong electrolyte. And then finally here with sodium nitrate, it is ionic, it's aqueous, it's one of the soluble ionic compounds, and so it is a strong electrolyte. And as we learned in the last section, so strong electrolytes dissociate into ions completely. And so the next version of this molecular equation we're going to write is called the Total Ionic, or just simply Ionic Equation. And what you do in that is that all strong electrolytes, you split them up into their cations and anions, because that's actually how they exist in the solution. And so in this case, we're going to have Pb2+, aqueous. We have two of these nitrates. So the 2 comes out in front now as a coefficient. We'll write them as separate ions. So plus 2 sodium ions here, and 2 iodide ions. But if you're not a strong electrolyte, you don't exist dissociated, so you don't write it that way either. You're just going to write this PbI2 just as it was. It's not a strong electrolyte. It doesn't exist dissociated. And then finally, our last strong electrolyte, will split him up as well. Cool. And this is what we refer to as our ionic equation, or sometimes complete ionic equation. And the only difference, again, is that all your strong electrolytes, we write them as fully dissociated, because that's actually a better reflection of what's happening inside that solution. So the lead and the nitrate aren't actually bonded together in this solution. They're floating around independently, since it dissociates completely as a strong electrolyte. All right, so if we look at this, we often call this a double displacement reaction, because it looks like two couples, went to a party and they traded partners and left with each other's partners. And that's kind of the way we look at it, and that's why it gets its name, either double displacement or double replacement. But that's not actually what's going on. We take a look at our ionic equation here, and you can see that actually you've got 4 singles went to a party. And 2 of them hooked up, and 2 of them just watched. And we call the ones that watched spectator ions. And that's why I come up with that lovely situation to kind of designate them. But they are the spectators. They didn't do anything. We looked at 2 sodium ions that are aqueous, came to the party alone. They left the party alone. They didn't do a single thing. Same thing with the nitrates. 2 nitrates came to the party alone. They left the party alone. They didn't do a thing. And we call them, again, these spectator ions. And when you eliminate the spectator ions, you get the last version of this equation that we need to write. And so the last version here, after you eliminate those spectators, Pb2 plus 2i minus going to Pbi2 solid. And this is now what we refer to as the Net Ionic Equation. And Net Ionic, it just says we're going to eliminate everybody who didn't do anything. All the ions that are spectators and don't do anything, let's just eliminate them out of the equation and see what's really going on. And so really it's just lead and iodide forming a solid precipitate here. And again, this is a precipitation reaction. Now you guys are going to be on the hook sometimes for just identifying the spectators or for deriving these Net Ionic Equations for all of our lovely double displacement reactions. So If you want to take a look, one thing you can see is that any ion, once you've identified who the strong electrolytes are, any ion that is part of a strong electrolyte on both the reactant side and product side is a spectator. So you could have gone back and said, oh yeah, nitrate's part of a strong electrolyte on this side and on this side. Same thing with sodium, part of a strong electrolyte on both sides, but not lead, strong on this side, not strong on this side, and not iodide, part of a strong electrolyte on this side, but not part of a strong electrolyte on this side. And so you can actually go through and identify those spectators pretty quickly, and also pretty easily see what that net ionic equation is going to be with just a little bit of practice. Cool. Now, as I mentioned in the last lesson, those solubility rules that flashed up on your screen here a little bit ago. Again, some of you are going to be on the hook for memorizing those. Your instructor should give you some guidance in that regard. But for many of you, you're just going to simply be provided with those, either looking them up in your textbook when you're doing homework, or like on the back page of your exam when you're taking your exam. So just make sure you know which situation you're in, but also make sure that you do get some practice with this, because identifying which compounds are soluble and insoluble, it's not hard, but you definitely want to make sure that taking your exam is not your first opportunity in doing so. All right, the second type of double displacement reaction we'll look at now is the acid-base neutralizations. Now, specifically, the kind of acid-base neutralization reactions we'll look at are going to be an acid, and then the base we're going to look at is always going to be a hydroxide base. Now, in second semester, we'll learn that not all acid-base reactions are going to look like this, because not all bases actually have a hydroxide, an OH, in the formula, and those are going to look a little bit different. But for now, we're going to focus just on this type of acid-base neutralization. When we do a double displacement reaction, H is going to go with OH, and for just a second, I'm going to write that as HOH. So, and then here, cation with anion, so Na with Cl is your other product. And there we go, and you should know that, yeah, H is +1, OH -1, so to speak, but HOH we don't write as HOH, it is water, and we would typically write that out as water in your final answer here for balancing this reaction. And so that's water, and water in an aqueous solution is the solvent, it's the liquid. So, and then NaCl, the look at solubility rules, is most chlorides, bromides, iodides are soluble, and the exceptions again are silver, lead, mercury, but that's not an exception, so he is soluble, and we'll write aqueous. And then to balance this thing out, it actually turns out it is balanced. All the coefficients are ones all the way across. Now, if we go through, I want you to identify these spectator ions, and let's get a net ionic equation. And so we'll start here. This is a strong acid with a strong base, back from back from the last lesson. And in this case, being a strong acid, strong base, they are two of the types of strong electrolytes. So we're going to label them as strong electrolytes, and they will exist in a fully dissociated state. So, and then NaCl is a soluble ionic compound, ionic and aqueous again, and so he is a strong electrolyte. But water is not a strong electrolyte. It is not a soluble ionic compound, not even an ionic compound. It's not a strong acid, it's not a strong base, therefore it doesn't exist in a fully dissociated state. All right, so then we can identify those spectators, which are part of a strong electrolyte on both sides, exist in a fully dissociated state on both sides of the reaction. And in this case, we can see that it's going to be chloride, part of a strong electrolyte on both sides, and then sodium is part of a strong electrolyte on both sides, but H plus and OH minus, not part of a strong electrolyte on both sides. And so what we're left with in our net ionic equation here, getting rid of those spectators, is simply H plus OH minus forming water. And again, that is our net ionic equation. Okay, so that's typically the way this works. So strong acid, strong base forms water and a salt. So, and as long as our base always has a hydroxide, our acid-base neutralizations are going to follow this pattern where they form water and a salt. And the salt doesn't mean it has to be NaCl. Technically, salt means any ionic compound. And so when you do an acid-base neutralization, you're typically going to get water and an ionic compound, water and a salt. All right, and again, in second semester, we're going to learn that not all acid-base reactions follow this pattern, but most of the ones you're likely to see at this point will. All right, now we had a strong acid and a strong base, but what is going to happen when we have a weak acid here? This is not one of your 7 strong acids. It's a weak acid. It does not exist in a fully dissociated state, and that's going to change some things when we identify our spectator ions and write our net ionic equation. So, but same thing here, H is going to go with OH, and I'm going to start by writing that out as HOH, and then Na with F. And in this case, water again is going to be a liquid, and we'll rewrite this in a second. So, and then NaF turns out not one of our solubility rules, but it turns out that all group 1 metal salts are soluble. So I'm going to give you this one, but he is indeed aqueous. But our solubility rules don't include fluorides, so sorry. All right, if we balance this, it actually turns out this one's also balanced. And so once it's balanced, so it turns out writing water as HOH for these double displacement reactions makes it easier to balance. Now, these weren't hard ones to balance because they end up being 1 to 1 to 1 to 1 all the way across. So, but we'll see one in just a second that's a little more challenging than that, and why I might write it initially as HOH. But you do want to, in the end, write it as H2O. And this is a balanced reaction. If we identify those strong electrolytes, again, HF being a weak acid is a weak electrolyte. It's going to exist in only a partially dissociated state, and usually that means like less than 5% dissociated. But NaOH is a strong base, and therefore a strong electrolyte. And sodium fluoride is a soluble ionic compound, and therefore a strong electrolyte. And that's it. Water again is not, and we learned that HF is not. And so if we go to identify our spectator ions, it turns out there is only one, and that is the sodium ion. Only sodium ions exist in the fully dissociated state on both the reactant and product sides, part of a strong electrolyte on both sides of the reaction arrow. And so that's the only one we can eliminate when going to the net ionic here. And so we're going to have HF plus OH minus aqueous, forming water and F minus. And that's our net ionic equation. Cool, this one trips up a lot of students. They're used to saying strong acid, strong base, and just reducing down to H plus OH minus forming water. So, but given the weak acid and deriving a net ionic, this is what trips a lot of students up, so I want to make sure I covered it here as well. So we want to look at one more example that's just a little more of a pain in the butt to balance, just so you've seen something like that as well. All right, this last one here, we've got phosphoric acid with sodium hydroxide. And I don't really care about getting all the way to the net ionic equation in this case. What I do want to get, though, is get a balanced molecular equation out of this. And so in this case, again, H is going to go with OH to form. And again, I'm just going to initially write it as HOH. So, and then the sodium is going to go with the phosphate. And in this case, sodium's +1, phosphate as a polyatomic ion is -3. And so the proper formula should have 3 sodiums for every phosphate. And there's sodium phosphate. All right, now we got to balance this thing. And the whole reason in writing the water as HOH initially is to make it easier to balance here. So if we look, we got 3 H's from the acid. Well, these 3 H's from the acid contribute the H in the HOH formula of water, whereas the OHs from NaOH, they're what contribute the OH part of the water formula there in writing it as HOH. And so that's going to make it, and recognizing that, it just makes it easier to balance. So when I see that I've got 3 H's from the acid here, well, the only way to get 3 H's from the acid here is to put that 3 out front. But that gives me also 3 OHs, and to balance that, I'll have to put a 3 out front here. And 3 sodiums, well, we've got 3 sodiums in the formula, and then 1 phosphate and 1 phosphate. And this thing's balanced, and now I can go back and write HOH as waters instead. And that's going to be a liquid, and it turns out, again, all group 1 metal salts like sodium salts are aqueous. And there we go. Cool. So if we tried to balance it by just writing water to begin with, a lot of students start getting lost and be like, oh, I got lots of oxygens in lots of places, and how do I balance this? But again, having written water initially as HOH, it's easy to keep track of where the H's are coming from the acid and the OH's from the base. So we've got one last type of double displacement reaction. This is going to be what I call a gas-forming reaction. Technically, this is actually going to be an acid-base reaction as well, just not one involving a hydroxide base. So I hesitate to call it an acid-base reaction, but HCl actually is an acid, and sodium carbonate here is a base. So, but I'm going to put it in its own class because it's going to look a little bit different, and it's going to be the only one that actually forms a gas as well. So we'll just call this a gas-forming reaction. And turns out there are actually 2 or 3 of these, but only one you're likely to encounter. So, and that's the one we're going to cover here. So if we trade cations and anions partners here, so H is going to go with CO3. So in this case, H is +1. Carbonate, though it's a polyatomic ion, is -2. So the proper formula should be H2CO3. And then Na is going to end up with Cl. Well, let's leave a little bit of room actually here because we're going to need it. And then let's balance this thing. And from here, we can see that we've got 2 sodiums on this side, so we'll need a coefficient of 2 in front of NaCl. That gives us 2 chlorides as well, so we'll need a 2 in front of HCl. That gives us 2 H's. We've got 2 H's, 1 carbonate, and this thing is now balanced. Now, the issue, though, is that what we formed here is carbonic acid. So in carbonic acid, spontaneously decomposes to give water and carbon dioxide. And so as soon as the carbonic acid forms in this reaction, it starts immediately decomposing to give water and CO2, and that is the gas that's forming. In fact, this is similar to the reaction you're doing when you might have made a volcano when you were a kid somewhere along the way, and you mixed maybe some vinegar with some sodium bicarbonate. And this is sodium carbonate, a similar substance, but sodium bicarbonate is just a little bit different, but ends up leading to the same place and forming carbonic acid, which decomposes, forming water and CO2, and that's the bubbling at the top of your volcano where you poured the red food coloring in with it to simulate lava and stuff like this. Cool. Now, because carbonic acid immediately decomposes to water and CO2, we don't view carbonic acid here as your product. We view the water and the CO2 as the product instead. And so we're going to go back up here and erase this and write water and CO2 instead. And that's actually your molecular equation. And so if you've got a double displacement reaction where you form H2CO3 carbonic acid, you're supposed to know that, oh, H2CO3 is not one of the products I actually write. I'll end up writing H2O and CO2 instead. Cool. Like I said, there are a couple of other gas-forming double displacement reactions, but you're just not likely to encounter them, so we're not going to take the time to cover them. One other thing to note, I don't want you to think that this is the only gas-forming reaction in the universe. Well, this is just the only gas-forming double displacement reaction you have to know. There are a lot of other reactions that form gases. They're just not double displacement reactions. So just don't think that we've identified the only type of gas-forming reaction. That's totally not true. It's just this is the example of a gas-forming double displacement reaction. Now, this is the part of the video where I say, hey, like and share and blah, blah, blah. You know what? Just smile, have a great day, get some practice in, and if you're looking for some good practice for your Gen Chem class, check out my General Chemistry Master course. I'll leave a link in the description. A free trial is available. Happy studying.